Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the wavelength and frequency at which the intensity of the radiation is a maximum for a black body at 2.7 Kelvin. So the first thing you have to note is that we're told to solve for the wavelength as well as the frequency at which the intensity of the radiation is at a maximum. So I'm going to write out the parameters. So we have the wavelength, which is just simply what we're looking for, and then the frequency, which is also what we're looking for. And we're told the intensity of radiation is a maximum for a black body at 2.7 Kelvin. We're also given temperature to be 2.7 Kelvin. Now, I want you guys to know this that this is a physical chemistry Atkins 11th edition question from the textbook, the Atkins Physical Chemistry 11th edition textbook, and we're dealing with quantum chemistry or quantum mechanics here. And whenever you have a quantum chemistry question that talks about intensity, talks about maximum, talks about radiation, what they want you to apply to solve any question like that is something you call the Wend's law, which simply says the wavelength at the maximum times temperature is going to equal a constant 2.9 times 10 raised to the power of negative 3 meter Kelvin. So what this is telling you is that this is basically the formula to solve for it. And when you're looking for wavelength at a maximum, you're going to use the Wend's law. And as you can see, the usually the unit for wavelength is meter. So you have this one here, and the unit for temperature is Kelvin. So you have this unit here. So basically, this whole all works. Now, this constant 2.9 times 10 raised to the power of negative 3 meter Kelvin is basically a constant called Wien's displacement constant. So this is called Wien's displacement constant. So now that you have all of this information, all you just do is simply rearrange the formula and substitute. So the wavelength at the maximum is just going to simply be 2.9 times 10 raised to the power of negative 3 meter Kelvin divided by 2.7 Kelvin. So now I also want to mention that they ask you to calculate the wavelength and frequency at which the intensity of radiation is at the maximum. So even though they just say wavelength, they're actually asking you to solve for the maximum wavelength. So we can just write maximum wavelength here. So basically, wavelength and maximum wavelength in this particular question is basically the same thing. So next, after we've written this, we just have to cancel out the Kelvin, cancel out the Kelvin. And when we cancel out the Kelvin, we can input this information in our calculator. 2.9 times 10 raised to the power of negative 3 divided by 2.7 is going to simply give you 1.0741 times 10 raised to the power of negative 3 meters. So that is it. But we are also chemists and we cannot leave our answer in the wrong number of sig figs. We have to put in the proper number of significant figures. And the proper number of significant figures is 2. So I'm going to round this up to 2 sig figs. So we'll end up with the wavelength at the maximum is just simply 1.1 times 10 raised to the power of negative 3 meters. So that's basically the answer to this part of the question. Now, the next thing we have to remember is that we're going to be dealing with frequency, which is the second part of the question. You see, we're told to calculate the wavelength and frequency at maximum, right? We've already successfully found the wavelength at the maximum. Now we have to calculate the frequency. And the formula we're going to be using is going to be C is equal to wavelength times frequency, or we can rewrite it here. C is going to equal wavelength at maximum times the frequency, since we're looking for frequency at maximum, where C is the 2.998 times 10 raised to the power of 8 meter per second. Now, this is the speed of light, right? And anytime you have a question where you have the wavelength, but you don't have the frequency, you can use the speed of light, the constant value, in order for you to determine. So the frequency now is just simply going to be the speed of light divided by the wavelength at maximum. So that's basically all you do. You substitute now 2.998 times 10 raised to the power of 8 meter per second divided by the wavelength at maximum. So 1.0741 times 10 raised to the power of negative 3 meter. So we cancel out the meters. So the frequency ends up becoming 2.998 times 10 to the power of 8 divided by 1.0741 times 10 to the power of negative 3. When you do that, you end up getting 2.79117 times 10 raised to the power of 11 meters. So that is basically the answer. But then again, we're chemists. We have to put our work in the proper number of significant figures. And the number of significant figures in this question is simply two sig figs. So we have to round up to two sig figs. So that would be the frequency at maximum will be 2.8 times 10 raised to the power of 11 meters. And this is basically the answer to this question. If you're confused about what I've done, please put in the comment section, ask me anything, or rewatch this video. And I also have another video like this on my channel where I also got the question from the Atkins Physical Chemistry 11th edition. So you guys should make sure you look into the description box, watch that video and rewatch this one as well in order for you to get the full grasp of it. So if you have any questions, suggestions or concerns, make sure you put it in the comment section. If you want me to tutor you physical chemistry or other STEM related courses, whether you're in middle school, high school or college, I am the tutor for you. I help students succeed in all their STEM related courses and also excel in academia. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.